Hello, good evening, and welcome to our presentation about analog optical Fourier techniques and specifically about image processing in medical applications. We are Maximilian Becker and Ignacio Wang from NTST and NTU respectively. Well, to begin, I will talk about the comparison from analog and digital image processing. Digital processing of medical image and computer-aided diagnosis have been studied extensively in order to improve the sensitivity and specificity that radiography needs for clinical diagnosis. The problem is that looking at the continuous future requirements that dramatically increase the speed and reduce cost of computing, the use of the current digital processing techniques can't be applied to other real-world situations. But we have another option, the analog optical processing. It manipulates image data in parallel. Thus, the processing speed is not a limiting factor. Therefore, it's important to understand the advantage and disadvantage of those techniques that for two-dimensional image processing in order to select the right method for medical image analysis and clinical diagnosis. So, why analog image processing? Because it has a faster process as it works at the speed of light and has a higher veracity achieved in high frequency. The digital advantages are that it has a high processing accuracy and it has the flexibility of programming. But for some applications, analog is preferred due to the high process speed and veracity, for example, for mammography. So the techniques that we are going to talk precisely today are going to be spatial filtering, which is the base for most of the following techniques, photoinduced anisotropy, and Fourier holography. All of these techniques are used for detection of abnormalities. For example, the one detected in mammography can be classified as masses, lesions, or microcalcifications. Features such as microcalcifications are often buried in background of soft dense breast tissues in a mammogram, resulting in low contrast between these essential features and the background. So, all these kind of abnormalities, due to the small size and diffuse nature of the human body, we will find that the edges have a really low intensity. So how do we find it? How do we find them? We use the conventional 4F optical configuration that we look in class. This one is called because the image is a distance from 4F, for focal distance from the image to the camera, and this configuration allows various spatial filters for blocking undesirable components in the Fourier plane, such as high pass filters, low pass filter, or band pass filters, such as the one in the image below.
So the next one we want to talk about is photo-induced anisotropy. Anisotropy in this case means the structural property of non-uniformity in different directions in the room or in the three-dimensional room. The basic principle in this case is intensity-dependent polarization rotation in combination with an rotatable polarizing analyzer that will selectively transmit the desired spatial frequency bands. For this, or especially in medical applications here, we use bacterial rhodopsin film, short BR film. This film has some dichroismic properties. That means that it absorbs one part of polarized light better than another one. As you can see in the picture, that's the basic arrangement of how this works. So we have like the polarizer for the incoming probe beam that polarizes the incoming beam. Then we have an actinic beam. Actinic in this case just means that it can cause a photochemical effect caused by radiation, or in this case light. So this beam comes in at an angle of 45 degrees and is also polarized. So the film in the beginning is not polarized, so it does not let light through. It's isotropic. That's what that means. When the incoming actinic light hits the film, it induces the polarization rotation. So the now polarized light can partly get through the film due to the film's dichroism. So, and then hits after that the analyzer, which will be important later. So we know when we have the probe beam and the actinic beam together hitting the film, some light gets transmitted through, and the degree of rotation of the probe beam polarization is dependent on its intensity. As you can see here, we have two graphs. The upper one shows the polarization rotation depending on the actinic beam intensity for a fixed probe beam intensity, and the second graph shows it the other way around, so the polarization rotation for a variable probe beam intensity while the actinic beam intensity is fixed. So we also know that in our case the most important thing is the things that are shown in graph 2, so where the probe beam is changing and the actinic beam is fixed. So you can see that the rotation polarization is high for low probe beam intensity and is low for high probe beam intensity. From the lecture we know that in the Fourier spectrum, low spatial frequencies correspond to high intensity, while high spatial frequencies correspond to low intensity. So, to get back to the second graph, on the left, the high rotation is low spatial, or is low intensity, so high spatial frequencies. And the rotation, the degree of rotation is low for high intensities, so low spatial frequencies. And sorry, we know that we can bring this back here in the next slide, which is about the spatial filtering. So as you can see in number 7, the incoming two beams hit the film, and after that they will go again through inverse Fourier lens, and after that through the analyzer. This analyzer, or this polarizing analyzer, is also rotatable, so we can rotate it, and with this select or change the frequency bands that get through and that we can filter for, that we want. We know that if the analyzer is 90 degrees towards the input beam polarization, we only get the high frequency components that get through, and that correspond in this case to the edges of our object, while low spatial frequencies, so the ones with no polarization, get blocked out. So by this, or by rotating the analyzer, or the axis of the analyzer, we can filter out the components we don't want and filter for the components of interest and the ones we want. So now to get to holography. So Fourier holography is, instead of spatial holography, it induces the record of our image onto the VR film in the Fourier plane, so recording the Fourier transform of the image. If we apply this method in the right way, it's possible for us to retrieve both the amplitude and the phase information of our original object. As you can see in the picture, that's the basic arrangement of such an experiment or such a method. So we have our laser that goes into a beam splitter, so it splits it into the reference beam. You can see it at M2, for example, and the object beam, which goes to the object, and after that both hit the second beam splitter, and after that the film. So both together, as said earlier, record the Fourier transformation of the image onto the film, and then the object beam is blocked and only the reference beam is left. The reference beam, together with this image that was saved into the film, can reconstruct our hologram with all the information that's in there. So with reconstructing, or first recording then reconstructing the hologram, we can retrieve all the information about phase and amplitude of our earlier image. So with this we can filter the things we want, and so we can only amplify the things we want to see, which results in a higher contrast image, which you can also see on the next slide. Also, one advantage is that all of this happens in real time, so it's a really quick process. Here you can see that the object beam intensity, if it matches the reference beam intensity, the diffraction efficiency is at its maximum, while if the object beam intensity is higher or lower than the reference beam intensity, the diffraction efficiency decreases. And the desired spatial frequencies can be selected by matching their intensity to that of the reference beam. So we can scan for the desired things by varying the intensity of our reference beam while the reconstruction phase, so while only our reference beam is active. So to the last thing that this has, so Fourier holography is also capable of looking at features at the different time scales. So we know that the enhanced components from earlier can be separated in time scale, so we can monitor different features at different times, because we know that different spatial frequency bands correspond to different intensities, and all of the bands exist simultaneously, but with different diffraction efficiencies. So, but we also know that the maximum efficiency only exists for one band. So this band at the optimum efficiency, it also lasts longer, as you can see in this picture. So we can filter over different time scale. For example, here at 0 seconds, all groups are displayed, so the low, the medium, and the high frequencies. And after 5 seconds, only the medium frequencies are yet or left that are good, visible in a good way. So those are the matching ones for the maximum efficiency. So those are our references. So thank you for your attention. And if you have any questions, you can ask.